Welcome to the deep dive. Today we're tackling a really foundational puzzle in physics. It's a paper that still, sends ripples through how we think about reality.
Mm-hmm.
Can quantum mechanical description of physical reality be considered complete? From way back in 1935. Einstein, Podolsky, and Rosen, the famous EPR paper.
That's a brilliant piece, yeah.
Mhm.
And you brought this to us, which is great, because this isn't just like the technical bits of quantum mechanics.
Right.
It digs right into what we even mean by real, doesn't it, at the very bottom level. So our mission today is really to unpack their main argument for you,
Okay.
to see why it kicked off such a huge debate, and, well, what it still means for how we look at the quantum world.
Exactly. So back in the 30s, quantum mechanics it was on a roll, right?
Yep.
Explaining atoms, subatomic stuff, doing great.
Yeah, racking up successes.
But Einstein,
Yeah.
well, he wasn't satisfied. He, along with Podolsky and Rosen, felt something was off, something missing.
Sort of incompleteness.
Yeah, they suspected that quantum mechanics, as it was, just wasn't giving the full picture, the complete description of physical reality. So this paper was their big push to argue for that incompleteness.
And they laid it out really clearly in the Physical Review, volume 47, page 7777, for anyone wanting to look it up. So for this deep dive, that paper is, well, it's our main source.
Got it.
We'll be pulling out their key definitions, their logic, and really walking through that iconic thought experiment.
Okay, let's jump in then. One of the first things they do, and it's super important, is define what they mean by an element of physical reality. Sounds simple, but it's like the philosophical core.
It really is.
They say, if without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity.
Right. That definition, that's the foundation for everything that follows. And the key bit, as you said, is without in any way disturbing a system. Think about it just, normally. If you can know something for sure, 100% certain, and you didn't have to poke or prod the thing to find out, it really suggests that property was already there, right? It was real, part of the system itself.
Right, like hearing thunder means there was lightning, even if you didn't see the flash yourself. You didn't cause it, but you know it happened.
Exactly, a good analogy. So EPR uses this definition as kind of the launching point to argue that quantum mechanics, well, it was incomplete.
Okay, so how does that lead to incompleteness?
Well, their argument connects to a really strange feature of quantum mechanics. The theory itself says you can't always know certain pairs of properties, like position and momentum, with perfect accuracy at the same time for one particle.
Ah, the uncertainty principle connection, or the precursor to it being used this way.
Sort of, yeah. The concepts are deeply linked. You can know position really well, but then momentum gets fuzzy. Or vice versa. There's a trade-off built into the math.
So the theory seems to say these properties are intrinsically linked in a way that limits our knowledge.
Right. But EPR pushes back. They say, hold on. If we can somehow predict one of those quantities, say momentum, with absolute certainty without disturbing the particle, then according to our definition, that momentum must be an element of reality. It has to exist with a definite value, even if quantum mechanics struggles to tell us about its positions simultaneously.
So they're suggesting the limitation isn't necessarily in reality itself, but maybe in the description provided by quantum mechanics.
Exactly. That's their core point. They felt reality should be, well, more solid, more defined than the quantum description seemed to allow, and this leads directly into their famous thought experiment, the EPR paradox.
Ah, yes, the paradox, the thought experiment that's caused so much head-scratching for nearly a century. Can you walk us through it?
Sure. So imagine you have two particles. Let's say they interact initially in some known way, and then they fly off in opposite directions. Quantum mechanics describes this pair, this whole system, with a single mathematical object, a wave function, even when they're miles apart.
Right, they're entangled.
They're entangled, exactly. Now, here's the clever part. Suppose we decide to measure a property of the first particle. Let's say we measure its momentum.
Okay, measure particle 1's momentum.
Because of how they interacted initially, and because of fundamental laws like conservation of momentum, measuring the momentum of particle 1 instantly tells us the momentum of particle 2.
Instantly. Even if particle 2 is, like, on the moon.
That's what the quantum formalism predicts, instantaneously. And here's where their definition comes back in. Since we can predict the momentum of particle 2 with certainty, And we did it without touching particle 2, without disturbing it in any way.
Right, we only measured particle 1.
Then according to the EPR criterion, the momentum of particle 2 must be an element of physical reality. It has a definite value. It was real all along.
Okay, I'm with you. That makes sense based on their definitions. So where's the paradox?
The paradox, or maybe the dilemma, comes when you realize we didn't have to measure momentum for particle 1.
Whoa.
We could have chosen to measure its position instead.
The other property from the pair.
Exactly. And because of the entanglement, measuring particle 1's position would instantly tell us particle 2's position.
Okay.
And by the exact same logic, using the EPR definition again, since we could predict particle 2's position with certainty without disturbing it, its position must also be an element of physical reality.
So wait, for that second particle, way over there, we could figure out its momentum, or its position, just by measuring the first one.
Correct.
And according to their definition, both that momentum and that position must be real, definite properties it possesses.
Yes, that's what their definition of reality seems to demand.
But quantum mechanics says you can't know both position and momentum with perfect certainty at the same time for the same particle.
Precisely. That's the rub. That's the core of the dilemma EPR throws down. We seem to have deduced that particle 2 simultaneously has a definite position and a definite momentum. Both are elements of reality. Yet the quantum formalism itself says you can't assign both definite values simultaneously within the theory.
Wow. Okay. So what are the options then? How do they resolve this apparent contradiction?
They lay out two possibilities. Option 1, the quantum mechanical description, the wave function, it's simply incomplete, meaning reality is richer than the wave function describes. There are facts about the system, like the definite values of both position and momentum for particle 2, that the theory just doesn't capture. These are the elements of reality missing from the description.
Okay, that's option 1. What's option 2?
Option 2 is, well, maybe the measurement on particle 1 does somehow instantaneously affect particle 2 no matter the distance, some kind of faster-than-light influence.
The spooky action at a distance.
Exactly. That phrase came later from Einstein, but that's the idea. A non-local connection, where measuring here instantly changes something over there.
And Einstein and his colleagues, they really didn't like that second option, did they?
Not at all. They considered it absurd, was the word they used in the paper. It seemed to violate the principle of locality, the idea that influences shouldn't travel faster than light. It just felt wrong, physically intuitive speaking.
So if they reject option 2, the spooky action,
then they're forced back to option 1. Their conclusion, stated right there in the paper, is inescapable for them. We are thus forced to conclude that the quantum mechanical description of physical reality given by wave functions is not complete.
that is a powerful conclusion. They're not saying quantum mechanics makes wrong predictions, are they?
No, that's a critical point. They weren't questioning its predictive success. It worked brilliantly for calculations. Their issue was with its ontology, what it claimed about the nature of reality itself.
Its completeness as a description.
Exactly. They believed reality had definite properties, whether we measured them or not, and quantum mechanics seemed unable to fully account for them without resorting to this, well, spooky non-locality.
So if the theory is incomplete, what did they think was missing? Did they have an idea?
The paper sort of hints at it, implicitly. It paved the way for what later became known as hidden variables.
Hidden variables.
Yeah, the idea is maybe there are some deeper properties, some variables associated with particles that quantum mechanics just doesn't know about or include. If we knew these hidden variables, maybe they would determine the outcomes of measurements in advance. Like the particle always had a definite spin, we just didn't know the hidden variable that dictated it until we measured.
So these hidden variables would restore a kind of classical determinism and definiteness to reality.
That was the hope, yeah. If these hidden variables existed and determined everything, then you wouldn't need probability waves in the same way, and you perhaps wouldn't need that spooky action at a distance either. Everything would be locally determined by these hidden properties.
It would fill in the gaps in the quantum picture.
That was the motivation behind exploring such ideas. The EPR paper didn't give a specific hidden variable theory, but it powerfully opened the door and really ignited decades of debate and research. It forced physicists to confront these really deep questions.
And for you, our listener, who brought this paper up, you can see now why it's just so pivotal, right? It forces us to ask these huge questions. Does reality exist when we're not looking? Is the universe fundamentally random? Or is there something hidden underneath? It seriously messes with our everyday intuition about cause and effect, locality, everything really.
Absolutely. And what's amazing is that this wasn't just, philosophical navel gazing. This very abstract thought experiment pushed physics forward. It led people like John Bell later on to figure out ways to actually test some of these ideas experimentally.
Right, Bell's theorem and the aspect experiments, testing whether reality is local or if the spookiness is real.
Exactly. It turned a philosophical debate into something that could be investigated in the lab. That's pretty remarkable.
It really is. It's one of those moments where theoretical physics just completely reshapes how we see the universe.
Yeah.
And yeah, it can feel maybe a bit overwhelming thinking about wave functions, entanglement,
Yeah.
hidden variables.
Right.
But the core logic of EPR, that definition of reality, the setup with the two particles, and the dilemma it presents, that gives you a really solid handle on why this debate is so important and ongoing.
And it highlights this fundamental tension, doesn't it? Between our classical intuition, things have definite properties, influences are local, and the bizarre, counterintuitive, but incredibly successful picture painted by quantum mechanics. EPR put its finger right on that tension point.
So wrapping it up for you, the listener, the EPR paper from 35 made a compelling case that quantum mechanics might be incomplete. Why? Because their definition of reality combined with entanglement seemed to imply particles possess definite properties, like both position and momentum, that the theory itself couldn't simultaneously account for,
Right.
leading them to conclude either the theory was missing something or we had to accept this spooky action at a distance.
And that leaves us with the profound questions they raised, which are still debated today. If quantum mechanics isn't complete, what's the hidden information? What deeper reality is it pointing towards?
Okay.
Or if locality isn't fundamental, if that spooky action is real, what does that imply about how interconnected the universe truly is? In ways that we're, still just scratching the surface
Right.
of.
And like we said, this paper was really just the start, the responses, particularly from Niels Bohr, and then later work like Bell's theorem.
Yeah.
That's where the story goes next. Definitely worth exploring if this has piqued your interest.
Absolutely. So thank you for bringing this paper to us. Your curiosity led us down a really fascinating path today into one of the absolute cornerstone debates in modern physics. It really shows the power of asking fundamental questions.